Hello, and welcome to Acoustics Derivations. In this video, we will be deriving the acoustic energy corollary and seeing how that relates energy density and intensity. So we begin by looking at the linearized conservation of momentum, which I'm going to just denote as M. Rho naught times du dt negative grad P. So we're assuming no body forces. So the first thing we're going to do is we're going to take the dot product of particle velocity u and the momentum equation. So we're going to take dot product of u and we write it like that. So we're going to take the dot product of u and m. Just like that. Well, the right-hand side of this equation is not very easy to work with. So we need to note the following. This is the product rule for multiplication by a scalar. So if we have scalar phi and vector A, then the divergence of phi times A is equal to phi times the gradient, times the divergence of A plus the gradient of phi dotted with A. Or you can rearrange that to say negative A dot grad phi is equal to phi divergence of A minus the divergence of phi times A. And you can kind of compare the right-hand side here, negative U dotted with grad P, and down here, negative A dotted with grad P. So we're going to make that substitution. When we do so, we obtain U dotted with rho naught du dt is equal to negative of the divergence of P times U plus P times the divergence of U. So we just took this and plugged it right on it. Okay, so we've used the momentum equation, and now we need to invoke the continuity equation. And specifically, we'll use the linear continuity equation, which is the following. The partial derivative of rho prime, and if you remember, rho prime is the perturbation off of the ambient density. So that's the perturbation density. So it's the time derivative of that plus rho naught, and so that's the ambient density times the divergence of u is equal to 0, which we can rearrange to obtain the following. Okay, so once we've obtained this, we can plug it in to here, and we obtain following. U dotted with rho naught du dt is equal to negative divergence of P times U. Make that P a little bit clearer. minus, and so we have this P right here that we're going to carry with us. So we have negative P over rho naught times the time derivative of the perturbation density. Now we need to start manipulating this a little bit. The first thing we'll note is that we can write U dotted with du dt as 1/2 du squared dt because we've assumed that u is a time harmonic function. And so this property holds. You can try it for yourself. Thus, we have that u times rho naught du dt can be written as rho naught over 2 times du squared dt, or this could be written as d dt rho naught over 2 times u squared. Okay. So that helps us with the first term. Now we want to take a look at the third term, this negative p over rho naught times d rho prime dt. To help us simplify this term, we'll look at the last equation used to derive the wave equation for fluids that we haven't used yet, namely the linearized state equation, which is the following. Okay, so it's pressure, which I should mention, this is the perturbation pressure, which we just treat as the pressure, what's interesting in acoustics, but you can see an earlier video on linearization, which discusses this. And so that's time, or that's equal to the perturbation density times the small signal speed of sound squared. And let's do some quick manipulation here to obtain an expression for rho prime. Well, if this is our expression for rho prime and we want d rho prime dt, then we can see that d rho prime dt is 1 over c naught squared dp dt. Okay, such that we have that negative p over rho naught times d rho prime dt can be written as negative p over rho naught c naught squared dp dt, which, using the same trick as we did up here, since pressure is also time harmonic, we have negative d dt times 1/2, or excuse me, negative d dt, and the derivative is 1/2 times p squared over rho naught c naught squared. Okay, so now we have all the building blocks. Let's take this equation here and make the substitutions, the simplifying substitutions that we were just talking about. And we obtain the following. And so we're almost there. We've almost derived the acoustic energy corollary, but we'll make two definitions first. The first one we'll define as intensity, I with a vector, And if you recall from the earlier video on this channel discussing intensity, you recall that intensity is defined as pressure times particle velocity, which we have right here. Okay. Well, we're also going to define energy density as rho naught u squared over 2 plus p squared over 2 rho naught c naught squared. Okay, and that might also ring a bell if you saw the previous video on energy density. Well, make the substitution and we obtain the acoustic energy corollary. The time derivative of energy density plus the divergence of intensity is equal to 0. This equation, the acoustic energy corollary, is consistent with the requirement of energy conservation in a fluid up to second order. It can also be written, if you are interested, in integral form as the following. Through energy arguments, we can also see that the components of energy density are the kinetic component and the potential component of the energy density. And I encourage you to watch the previous video on energy density to see how this was obtained. But you can kind of look, at least for the kinetic component, you can kind of see how this term resembles 1/2 mv squared. But of course, now we're in energy density, so you would divide by volume. So 1/2 rho u squared, which leaves the other term, p squared over 2 rho naught c naught squared, to be the potential energy density. The acoustic energy corollary can tell us a couple things that we knew before, but were just kind of presented to us or not rigorously shown, per se. The first one is, let's consider a plane wave defined, and discuss the particle velocity, I should say, in the following way, where n is the direction of propagation. Well, we see then that epsilon over 2 is 1/2 rho naught u naught squared, which is equal to 1/2 p squared over rho naught c naught squared. In other words, for a plane wave, we write plane wave here, the kinetic energy density and the potential energy density are equal, and they're equal to half the total energy density. Well, we can also see that intensity is equal to this by intensity is P times U, which we can then relate to energy density by saying C naught times the direction of propagation times energy density. Rearranging, we have that intensity divided by energy density is simply speed of sound times the direction of propagation. What this means, or what this implies, I should say, is that acoustic energy moves as a sort of unit with speed c naught in direction n. Thus, c naught, we can say, is the speed at which the acoustic energy travels for this case. Another interesting result of the acoustic energy corollary is the fact that we can obtain expressions for power radiated by a source from the corollary. To do so, we're going to assume that, the terrible P, we're going to assume that P and U are of the form some complex amplitude P or U, which I've denoted complex amplitude by a tilde above, times an e to the minus I omega t or e to the j omega t, whichever you choose. So as we saw above, since epsilon energy density and I intensity are both quadratic in the field variable, it follows that each must be of the form of the sum of a time-independent quantity plus a quantity oscillating in time with angular frequency 2 omega. So let's look at the time averages of energy density and intensity. So if we take the time average of energy density, we see that is 1/4 times rho naught times u, the complex amplitude of u, times the complex amplitude of u, or I should say dotted with, plus 1/4 times the complex amplitude of p squared, take the magnitude of that, divided by rho naught c naught squared. And we also have the time average of intensity is 1/2 real p u, and then star, where star indicates complex conjugate. Now, this term on the right looks or should look very familiar to you, as this is the definition, or I guess the definition of intensity is P times U. But in this form, this is how we calculate intensity. And we've shown that before in the video on intensity. Interestingly, if you take a time average of the time derivative of epsilon, that turns out to be 0. Since the averaging time is either, it turns out to be either an integral number of half periods, which would mean it would be 0, or it's a very large interval, which we can then treat it as 0, the time derivative. If you appeal back to the acoustic energy corollary and take the time average of it, all you're left with is the divergence of the time averaged intensity is 0. Or if you are integrating over some surface, we see that the integral of the time averaged intensity dotted with the outward normal n, so earlier n was the direction of propagation, now it's the outward normal, that turns out to be equal to 0. Unless if S encloses a source, then we obtain time averaged acoustic power radiated by a source. So as long as S encloses the same source, the power computed according to the above or to this equation here is independent of the shape and size of S. And if you take a look at this, you would recognize this equation as well, being the equation for acoustic power radiated by the source. So that concludes this video. Thank you.